You may have probably experienced the effects of electric charges directly if one day you notice the cling between your clothes when you remove them from the dryer. Or if you ever felt a spark when touching something like a doorknob after walking on a carpet. And our home devices all work using electric power. And so the phenomena of electricity and magnetism plays a central role in everything around us because all atoms are made up of positively charged protons and negatively charged electrons and neutral neutrons. So you may charge objects yourself. For example, if you run a comb through your hair, it can then attract bits of paper. And another example is that if you rub a balloon with wool, especially on a dry day, the balloon can stick on the wall. So experiments show that there are two kinds of electric charges, positive and negative. So suppose you rub a rubber rod with fur and you rub a glass rod with silk and you bring them close to each other, as you can see here, then the two rods will attract. While if you rub two rubber rods with fur or two glass rods with silk and you bring them close to each other, they will repel. So this shows that the rubber and the glass rod each have two different kind of charges. The electric charge on the glass rod was given the name positive, while the one on the rubber is negative. And the experiments show that charges of the same sign repel, while those of the opposite sign attract. And there are only two charges because any unknown charge found that is, for example, repelled by a negative is always attracted to a positive and vice versa. And there was never found or observed any third charge that is attracted to both positive or negative or repelled by both. So there are only two kinds of charges, just positive and negative. And so we will now discuss two properties of electric charge, which is the conservation of charge and the quantization of charge. In an isolated system, the net charge is always conserved. So, for example, if two neutral objects are rubbed together, the objects become charged because electrons transfer from one object to the other. So, this means that charge is not created in the process. Instead, one object receives the electrons, gaining a net negative charge, while the other loses the electrons. So it loses an equal amount of negative charge, and as a result, it acquires a net positive charge. Okay. So if these two objects are isolated from the surrounding environment, no transfer of charge occurs across the boundary. So, for example, when a glass rod is rubbed with silk, as in the previous example, electrons transfer from the glass to the silk as a result, and so the silk obtains a negative charge while the glass is left with a positive charge. The same way, when a rubber rod is rubbed with fur, electrons are transferred from the fur to the rubber, and so the rubber gains a negative charge while the fur is left with a positive charge. And the neutral object contains an equal number of electrons and protons, and so the net charge of a neutral object is equal to 0. So another property of electric charge is that the total charge is always an integral multiple of an elementary charge E, that is equal to 1.602 times 10 to the minus 19 Coulomb. And this is because any amount of negative charge is a result of the combined charge of an integral number of excess electrodes, where the charge of each electron is given by this value. and any amount of positive charge is the result of the deficiency of an integral number of electrons, or it could be a number of protons together, and so this is where the quantization of charge comes from. Okay. We will now discuss insulators and conductors. So the ability of a charge to move within a material is known as electric conduction. Materials are classified in terms of the ability of charges to move within a material. So electric conductors like metals are materials in which electrons can move freely throughout the material, and this is because a metal contains one or more outer electron in its atom that is weakly bound to the nucleus of the atom. So when many of these atoms come together to form a metal, the outer loosely bound electrons become free electrons, and they can move freely about the metal in a way similar to how gas molecules move in a container. Okay. Electric insulators are materials in which the atoms do not contain outer weakly bound electrons. Instead, all electrons are bound to the atoms, and therefore they cannot move freely throughout the material. Examples of insulators are glass, rubber, and wood. And when an insulator is rubbed, like in the previous example of rubbing a glass or rubber rod, only the rubbed area becomes charged because the charge in such materials cannot move freely to another part of the material, such as in the case of a metal. So, for example, when electrons are transferred from the fur to the rubber rod in the previous example, they stay localized at the rubbing site because rubber is an insulator, okay? And the electrons are not free to move to another region. Examples of good electric conductors are copper, gold, silver, and aluminum. When a conductor is charged at a certain region, the charge distributes itself over the entire surface of the material because in a conductor, charge can move freely. Okay. So to understand this further, consider, for example, that you rub a copper rod with fur and try to attract small pieces of paper with it, like in the case of a comb, attracting pieces of paper. You will notice that the copper rod will not attract the pieces of paper, and this is because the electric charges produced by the rubbing will move freely throughout the copper rod and then through your body, because your body is also an electric conductor, and finally to the earth. Okay. But if you hold the copper rod with an insulating material and then rub it with fur, the rod will remain charged, okay, and it will attract pieces of paper. Third class of materials classified in terms of electric conduction are semiconductors. The electric conduction in a semiconductor lies somewhere between a conductor and an insulator. The charges in a semiconductor can move relatively freely, but way fewer charges move in a semiconductor than in a conductor. And this can be changed by many orders of magnitude by adding certain amount of foreign atoms to a semiconductor, which then will change its electric properties. And so semiconductors are flexible materials in terms of their electric conduction abilities when we add, because we can add foreign atoms and change their properties. Examples are silicon and germanium, which are used in electronic devices. So when a conductor is connected to Earth through a conducting material, it is said to be grounded, okay? And the Earth can be considered as an infinite reservoir of electrons where it can give or accept an unlimited number of electrons. So to understand charging by induction, let's consider a metal sphere that is uncharged, which means it's neutral, and suppose that it is insulated from the ground. And now suppose that you charge a rubber rod by rubbing it with fur and you bring it close to the sphere. Then the electrons in the region nearest to the rod will move to the opposite side of the sphere because they will experience a repulsive force from the negative charge of the rod, and so the side of the sphere that is near the rod here will acquire a net positive charge. Okay. And so note that only the electrons in a metal are free to move, okay? And also note here that the rubber rod does not have to touch the sphere for this movement of the electrons in the sphere to occur. And now, suppose we repeat the experiment, but we connect the sphere to the Earth by a conducting wire, and shown by this symbol, which means that the wire is connected to the ground. And now, suppose we repeat the experiment and bring the charged rubber rod close to the sphere. Then some of the electrons in the sphere will be strongly repelled by the negative charge on the rod, that they will move out of the sphere through the wire and into the earth. Okay, and if the conducting wire to the ground is then removed, the sphere will be left with a net positive charge because of the deficiency of electrons it has now. So there aren't enough electrons now to cancel the positive charge of the protons. And you see that the sphere acquired a net positive charge. And if we remove the rubber rod from the vicinity of the sphere, so the induced positive charge will remain on this conducting sphere. Okay, and so this is charging by induction, and a similar process can also happen in insulators if a charge is brought near an insulator. Okay. So, in most neutral atoms and molecules, the center of the positive charge and the center of the negative charge coincide. So, suppose we have here an atom, the center of the positive nucleus and the center of the electron cloud coincide. And so the atom or the molecule is said to be unpolarized, okay? But when a repulsive or attractive force from a charged object is present, so these centers may shift slightly, resulting in a more positive charge on one side of the molecule or atom than the other side. And this is known as polarization of a molecule or atom, and can, as you can see here, it can produce a layer of charge on the surface of an insulator. So when a charged balloon here is brought or is placed on a wall, the negative side of the polarized molecule, so the molecules will become polarized, and the negative side of the molecule is closer to the positively charged balloon than the positive side of the molecule. And so the attractive force between the positive and negative charges here, the attractive force is larger than the repulsive force between the positive charges, and this will result in a net attractive force between the balloon and the wall. So we will now discuss Coulomb's law. So Charles Coulomb used the torsion balance to measure the electric forces between charged objects quantitatively. And the torsion balance is similar to the one used by Cavendish to measure the gravitational force between objects. Okay, the electric force is much larger, of course, than the gravitational force, so any gravitational attraction here can be neglected. Coulomb found that the electric force between two small charged spheres causes the spheres to either be attracted to each other or repelled, and the resulting motion will cause a suspended fiber to twist. And the angle of rotation can be measured using a laser beam. The details of how the torsion balance works can be found in any textbook, and we will not discuss it here. Coulomb found that the electric force between the two charged particles is inversely proportional to the square of the distance between them, and it's also directly proportional to the quantity of charge on each sphere, and he established Coulomb's law. And note here that we consider the small spheres as particles, so we use the particle model of an object that we discussed in the videos of mechanics. And this is possible for charged objects that are very small compared to the distance between them, okay? And so we can consider them as particles and apply Coulomb's law. And so Coulomb's law states that the magnitude of the electric force between two-point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Okay? And this is known as Coulomb's constant, and the force is in Newton if the charges are measured in Coulomb and the distance in meter. And Coulomb's constant can be written as 1 over 4 pi epsilon naught, and epsilon naught is the permittivity of free space, and it has this value, okay? And so the direction of the force depends on whether it is attractive or repulsive, which of course depends on the sign of the charges. So as you can see here, the force on charge 1 from 2 is in this direction, and the force on 2 from 1 is in that. Here it is a repulsive force, and here it's attractive. And if you remember that one electron, the charge of one electron is 1.602 times 10 to the minus 19 Coulomb. So if we want to know, because charge is quantized, so if we want to know how many electrons are in 1 Coulomb, we divide 1 Coulomb over 1.602 times 10 to the minus 19 Coulomb, and we get 6.25 times 10 to the 18 electrons. So there are 6.25 times 10 to the 18 electrons in 1 Coulomb. And so 1 Coulomb is a large amount of charge, and usually in electrostatic problems, the amount of charge is of the order of micro Coulomb, okay? So, going back to the direction of F, so when you solve electrostatic problems, it is important to draw the force on each particle from all the other particles. So a pictorial representation is really important in electrostatic problems to be able to analyze it and find the resultant force. So the electrostatic force exerted on particle 2 by 1 is given by this equation. So the force on 2 by 1 is in the same direction of the unit vector R12, okay? So the unit vector R12 is directed from particle 1 to 2. And of course, you know from Newton's third law that F12 is equal to minus F21. And that is from Newton's third law. So this expression here shows that if Q1 and Q2 have the same sign, the product Q1 Q2 is positive and the force is repulsive, while if they have opposite signs, the product is negative and the force is attractive. Okay, and so if you have, let's say, a particle surrounded by 3 other particles, So the resultant force on, let's say, particle 1 is the force on 1 by 2, the force on 1 by 3, and is plus the force on 1 by 4. And this is the principle of superposition, and this is how you find the resultant force on the particle, okay? So let's see some examples here. So first, let's say we have three positive charges, Q1, Q2, and Q3, and Q1 and Q2 are separated by a distance d, and you want to know where you can place Q3 between the two charges such that the force on Q3 vanish, okay? So the force on Q3 is, the net force is equal to F31 minus F32. So F31 is the force on 3 from 1, and it's repulsive, that's why it's in this direction, and Q3 is also repelled from Q2, so the force on 3 from 2 is in this direction. And so since we have only one direction, we can remove the vector notation, and we get for F31 it's Q1 Q3 over x squared, okay? And F32 is Q2 Q3 over d minus x squared is equal to 0, and this gives the expression for x, which is where we can place Q3 so that the force on Q3 from the two charges vanish, okay? So let's suppose we have also another example, the hydrogen atom. So the hydrogen atom has one proton and one electron. And let's say we want to find the electric force between them, and if the average separation between them is 5.3 times 10 to the minus 11 meter. Okay, so we calculate the electric force, and it's equal to 8.2 times 10 to the minus 8 Newton. So as we mentioned in the videos of mechanics about field forces and contact forces, the electric force is a field force that can act through empty space and no physical contact is needed for it to act. And this is where the concept of a field comes from. So, for example, if we have a charged object, it has an electric field around it, and this field can be felt by a test charge that is placed in the vicinity of this field, okay? So the object producing the field is known as a source charge, and the test charge is positive and small enough so as not to disturb the electric field of the source charge. So this charge is much larger than the test charge. The electric field due to the source charge at a point P is defined as the electric force per unit charge experienced by the test charge at that point, okay? So the electric field vector E at a certain point in space is defined as Fe vector over Q naught, and Fe is the force acting on a positive test charge Q naught. And so the SI units of the electric field is Newton per Coulomb. The direction of E, as you can see, the direction is in the same direction of the force experienced by the positive test charge at that point. So the test charge here is repelled by this charge, so the force is in this direction, and so is E, it's in the same direction. And also you can see that E depends only on the source charge, so it is a property of the source charge, because Q naught here will go with Q naught, and we are left with the source charge. So if the electric field at a certain point is known, and you want to find the force on any particle of charge Q, not necessarily a test charge, but any particle, then F is equal to QE. So now let's consider a point charge located at distance r from a test charge Q naught. So imagine here at this point there's a test charge Q naught. The electric force between Q and Q naught by Coulomb's law is given by this equation, okay, where this R hat is a unit vector directed from Q to Q naught. The electric field at the position of the test charge, so imagine we remove, so the test charge is here, but I'm not showing it here, but the electric field then at this point is given by KEQ over R square R, because Q naught goes with Q naught, okay? So we are left with the source charge. So as you can see, if the source charge is positive, the electric field is directed away from the source charge. If it is negative, the electric field is directed towards the source charge. So the electric field, let's say we have a point here, P, and there are a number of point charges surrounding it. Then the electric field at that point is the vector sum of the electric fields at that point due to all the individual point charges, okay? And so E is equal to KE sigma QI over RI square RI hat, and RI is the distance from the ith charge QI to the point P, at which we want to calculate the electric field, and RI hat is a unit vector directed from QI to P, okay? So we will now consider the example of an electric dipole. So an electric dipole consists of two charges that are equal in magnitude. One is a positive point charge and the other is a negative point charge, and they are separated by distance. Here it is 2a. So the dipole is very important in physics as it plays part in many things. And many charged systems can be approximated either as a static dipole or an oscillating dipole if they are oscillating, okay? So, for example, we will see in other videos that in an external electric field, neutral atoms and molecules behave as dipoles. For example, in an oscillating electric field of electromagnetic radiation, such as visible light, they behave as oscillating dipoles. And other molecules are also permanent dipoles, such as the HCl molecule. And so we will discuss in other videos how induced dipoles or permanent dipoles behave under the influence of an external electric field. Okay. So here we have two source charges, so we may use the equation here where I is equal to 2. And you will see that in many problems of electricity and magnetism, the symmetry of the problem can really simplify it. So for example here, since plus Q is equal to minus Q, the vector E1 is equal to E2, okay? Why? Because P is at the same distance from both the charges, which is the distance is R. And so the total field at P is E is equal to E1 plus E2. But from symmetry, you can see that the Y components of E1 and E2 are equal in magnitude and opposite in direction. So this is the Y component of E1 and this is the Y component of E2, and they are equal in magnitude, opposite in direction, so they cancel each other out, okay? And the X components are equal in magnitude and have the same direction, so they add up. So let's first see the magnitude of the vector E1. So the magnitude is just KEQ over R square, which is KEQ Y square plus A square, okay? And the total total is equal to E1x plus E2x, which is 2E1x, and E1x is equal to magnitude of E1 times cosine theta. So 2ke q over y squared plus a squared cosine theta, which is a over r, so a over y squared plus a squared to the power half. And this gives E, the total electric field at point P is the magnitude of it is ke 2qa y squared plus a squared to the power 3 over 2. And its direction is in the x direction, okay? So let's now find the electric field at a point y that is much larger than a, so far from the dipole. You can see that the electric field, so we can neglect this term, and the electric field is equal to ke 2qa over y cubed, okay? So you can see that this equation here, it gives the value of the electric field on the y-axis, because we chose P on the y-axis, so it gives the value of the electric field for all points on the y-axis. So the electric field is directed along the x-axis, and it's parallel to the axis of the dipole. And you see here that for points that are far from the dipole, the field of the dipole drops with y cube, so it is proportional to 1 over distance cube. But for a point charge, for a 1 point charge, it is proportional to 1 over distance squared. Okay, so it drops faster, it diminishes faster in value as we go further for a electric dipole than a point charge, and this is because at distant points the fields of the dipole the fields from the two charges of the dipole almost cancel each other out, okay? So we will now discuss the electric field due to a continuous charge distribution. So if the average separation between source charges is small compared to the distances from a point P in which we want to calculate the electric field at, then in that case the system of source charges can be considered as a continuous charge distribution over some volume or surface instead of a discrete system of charges. So we consider the system of source charges as one charged object, as a continuous charged object, okay? So to calculate the electric field due to a continuous charge distribution at a point P, as you can see, the charge distribution is first divided into small elements, each of charge delta Q. The electric field due to this element at point P is written as delta E. So delta Q2 produces delta E2 and so forth for each source charge at the point P. So the total field at P is then the vector sum of the fields produced from all the elements. And so we have delta EI from one element is equal to Ke delta Qi over Ri square, Ri hat, where this is a unit vector extending from the charge element to P. And the total electric field E will be the sum. So the sum of the contribution from all the charge elements. So if the elements of charge are infinitesimally small, so if delta Qi goes to 0, we have the total electric field at point P due to a continuous charged object is equal to Ke integration dq over r square r, okay, r hat. So dq is an infinitesimal amount of charge. So you can see there's a vector in the integral here, but in problems that has some symmetry in the charged object shape, the problem can be simplified and the integral can be reduced to a scalar integral that does not contain any vectors, okay? So we will consider now examples in which the charge is uniformly distributed over a line, surface, or volume. And for that, we use the concept of charge density, that is a constant density, so it's not a function of any dimension. So a constant volume density is equal to Q over the volume of the object, Coulomb per meter cube, and this is the surface charge density, Q over A, the area of the object, Coulomb per meter square, and this is the linear charge density lambda, which is Q over L, Coulomb per meter, okay? So let's see some examples here of charged objects. So let's first consider a rod of length L, a uniformly charged rod of length L. So it has a uniform positive charge density per unit length lambda, okay? And the total charge Q, capital Q, okay? So let's calculate the electric field at a point P along the x-axis, a distance of A from the end of the rod, okay? So because each charge element dq produces an electric field dE, that is directed in the negative x direction because it's a positive charge, okay? The resultant electric field will also be in the negative x direction, and so we can calculate the total electric field without the need of vectors, okay? Because all the elements are in the electric fields from all the charged elements, they all are directed in the negative x direction. And so we have dq for a charge element, dq يساوي lambda dx, the length of the charge element is dx. And so d is equal to ke dq over x squared. And from that we integrate. So x, it changes from a to a plus l. And we integrate and we substitute for lambda q over l. And this gives us for E, the total E at P is KEQ A over A plus L. And so let's say P is really far from the road, that A is much larger than L. So A is much larger than L. Then we can neglect L here, and E is equal to KEQ over A square. And this is equivalent to a point charge of charge Q and distance A, okay, from P. So at a large, really far away from the road can be equivalent to like a point charge. Let's consider another example of the electric field of a uniformly charged ring of radius A and total charge Q. So we want to calculate the electric field at a point P along the x-axis that passes through the center of the ring and is perpendicular to the plane of the ring. So as you can see, the electric field due to a charge segment dq is dE, and it can be resolved into two components, dE perpendicular and dEx, okay, along the x-axis. And so a charge element from the opposite side of the ring will give us here dE2, and also can be resolved into two components. And you can see that the two perpendicular components from the two opposite pairs, they cancel each other out, right? So they the perpendicular components cancel each other out, and we are left with the all parallel components. They add up, and this is an example of how symmetry simplifies the problem. So if we include all segments pairs from all the ring, then all perpendicular components of the field cancel out and the parallel components all add up. Uh, so total dx is equal to ke dq over r squared cosine theta, and r squared is x squared plus a squared, and cosine theta is x over x squared plus a squared to the power half, okay? And this gives us this expression for dx, and if we integrate, so we integrate here, and because all segments are at equidistance from the point P, so they contribute equally to the field, and we can put this out of the integration, and we integrate dq is equal to q, and we get this expression for the total electric field at a point P along the x-axis that pass through the center of the ring. And so if the distance from the ring is really larger than the radius, so it's really far from the ring, then Ex is equal to Keq over x squared. And this is, as in the case for the rod, at a large distance from the ring acts like a point charge, okay? We will now consider electric field lines, which help to visualize the electric field. So at each point, the electric field vector is tangent to the electric field line, okay? Also, the number of electric field lines per unit area through a surface that is perpendicular to the lines is proportional to the magnitude of the electric field there. So if E is large, the electric field lines are close together, and if it's small, the lines are farther apart. Okay, so as you can see here, the density of lines through this surface is greater than through this one. And so the magnitude of the electric field here is greater than the magnitude of the electric field here. So also note that if an electric field is uniform, it means that the electric field vector, so it will have the same magnitude and direction at each point, and the electric field lines will all have the same direction. But as you can see here, the field lines here point in different directions, so the electric field here is non-uniform. So the figure here shows the electric field lines of a positive charge and a negative point charge, but here only the field lines lying in the plane of the page are shown. But of course the lines extend radially outward or inward in all directions. So for a positive charge, if we place a positive test charge here, the electric force on it will be directed away from the positive charge, and so the electric field is directed away from the positive charge, okay? Because the positive test charge is repelled by this charge, and the positive test charge will be attracted to this charge, so the electric field vector is directed towards that charge. And so in both cases, the lines are radial and they extend to infinity. Note also that as we come closer to the charge, the lines are closer together, which means that the magnitude of the electric field increases as we go closer to the charge. And it decreases as we go away from the charge because the lines become farther apart. Okay, so to understand this point further, consider here an imaginary sphere of radius r, okay, that is concentric with the charge. Then from symmetry, you can see that if we have an imaginary sphere, the magnitude of the electric field is the same everywhere on the surface of that sphere because each point is at the same distance from the charge, right? And the number of lines per unit area on the sphere is n over 4 pi r square. And 4 pi r square is the surface area of the sphere. So because E is proportional to the number of lines per unit area, it means it is proportional to 1 over r square. And this is consistent with the equation E is equal to KEQ over r square for a point charge. Okay? So when drawing electric field lines, the lines must begin on a positive charge and terminate on a negative charge. Also, the lines should not cross, and also the number of lines from a charge should be proportional to its magnitude. Okay. So here this shows two equal point charges that are opposite in sign, and the number of lines that begin at the positive charge is equal to the number of lines that terminate at the negative charge. And the region, as you can see, the region in the middle here has a high density of lines, and so it is a region of a large electric field. Okay, and this one shows two positive charges that are also equal in magnitude. Because they are equal in magnitude, the number of lines emerging from both is equal. Okay. Also, at a far away distance from both the two charges, the field is approximately equal to that of a single charge of plus 2q. So if we go really far from these two charges, the field can be approximated as a single charge of plus 2q. Okay. And this shows two charges that are not equal. One is plus 2q and one is minus q. And as you can see, the number of lines leaving plus 2q is twice the number entering minus q. Okay. And also, if we go at a really far distance from both the charges, the electric field is approximately equal to that of plus 2q minus q, which is equal to plus q. So it's equivalent to plus q. At large distances, we can approximate it as plus q. Okay? So let's consider now motion of a charged particle in a uniform electric field. So if a particle of charge q and mass m is placed in an electric field E, then the electric force on the charge is Fe is equal to QE. And from Newton's second law, this is equal to Ma, and so A is equal to QE over M. Okay, so if E is a uniform field, which means it has a constant magnitude and direction, as is the case here, okay, then A is constant, so the acceleration is constant. So as you can see, if the particle has a positive charge, it will accelerate in the direction of the electric field, and if it has a negative charge, it will accelerate in the opposite direction to the field. Okay. So in this example, we have two parallel plates of opposite charge, and this test charge is released from rest here. And as we said, because the field is uniform, it will experience a constant electric force and therefore a constant acceleration, and it will accelerate towards the negative plate. Okay. So if we want to find the speed of the particle after it has moved a distance d, we can use the kinematic equation, this one, and from this we can find v final. Okay, so this is v final. We substitute for a, and we get v final. Okay, so alternatively, we can use the work energy theorem. So the work done by the electric force on the charge is equal to the change in its kinetic energy So the work done is FED after it has moved a distance d, and its K initial is 0 because it was released from rest, and this will give the same final velocity as if we use the kinematic equation, okay? So now let's suppose an electron enters the field with an initial velocity that is perpendicular to the field lines. So in this case, the motion is two-dimensional, okay? And the electron follows a curved path, okay? So as in the previous example, a constant electric force is exerted on the electron and its direction is in the negative y direction. So even though the field is in this direction, the force is in the negative x direction because it is a negative charge, as we said here. Okay, so if it's negative charge, it will be the electric force directed opposite to the field. And so the electron experiences a constant acceleration in the negative y direction given by this equation. And you can see that you can use the kinematic equations just like the ones used for a projectile motion under gravity to find, for example, if you want to find the time it takes the electron to leave the field or the vertical distance it has traveled, okay? After traveling a horizontal distance of L, how much is, you can find what is the vertical distance it has traveled from its initial y position. So we will now discuss electric flux. So electric flux is a quantity proportional to the number of lines penetrating a certain surface. So consider a uniform field that is constant in both magnitude and direction passing through this surface, okay? The electric flux in this case, phi E, is given by EA and its SI units is Newton per meter square over Coulomb. So A here is the area of the surface. So you can think of flux in terms of field lines passing through A. So if we increase A, it means more lines of E will pass through, which will increase the flux, right? And if we increase E, so we have a stronger electric field, it means the field lines are more closely spaced and therefore there will be more lines per unit area, which again will increase the flux, okay? So if the area is not perpendicular to E, as you can see here, then fewer lines pass through. And in this case, the area that counts is the projected area A perpendicular, which is equal to A cosine theta. And the electric flux of a uniform electric field is given by this equation, okay? So theta here is the angle between the normal to the surface. This is the normal to the surface and E. And so the flux has a maximum value when theta is equal to 0, which means the normal to the surface is parallel to E, like in this case. Or we can also say the surface is perpendicular to E, right? And if theta is equal to 90 degrees, which means the surface is parallel to the field, then the flux is equal to 0. Now let's consider the case when the electric field is not uniform but vary in both magnitude and direction over the surface. Then we can divide the surface into a large number of small area elements, okay, each of area delta AI. And if this element is small enough, we can ignore the variation of E over it, right? So we can define this vector delta AI as the area of the ith element whose direction is perpendicular to the surface at that point. So delta AI, it is directed in different directions for various surface elements. And the electric flux is then given by delta phi E is equal to this, and this is the dot product between the vector EI and delta AI. Okay, and if we sum over all the elements, we get the total flux through the surface. Uh, and if we let the area of each element approach zero, then the number of elements approach infinity, and we can replace the sum by an integral. And so we get this equation. It is the integration over the surface. So this is a surface integral evaluated over the area in question. Okay, this is the electric flux for a varying field. For a closed surface, we write the closed integration of E dot dA, and this is equal to En dA, and En is the component of E normal to the surface. Okay. The net flux through a surface is proportional to the net number of lines penetrating the surface, okay? And this number is equal to the number of lines leaving the volume surrounded by the surface minus the number of lines entering the volume surrounded by the surface. So if more lines leave than enter, the net flux is positive. If more enter than leave, the net flux is negative. And if the number of entering and leaving lines is equal, then the net flux is equal to zero, okay? So let's consider this example. So we have a uniform electric field that is constant in both magnitude and direction, and we want to find the electric flux through a cube. And so we write phi E is equal to closed integration of E dot dA. But you can see that the electric field lines are perpendicular only to two faces, which is this face 1 and 2. And actually it is parallel to all other faces. So this, and this, and this, the electric field is parallel, so the flux through these surfaces is zero. So there is only flux through this one and this one. And so we have this integration. We are left with integration of E cosine 180 degrees dA, which is the flux through surface 1. So dA and E is in opposite directions, so the angle between them is 180 degrees. And for this surface, it's E cosine 0 dA, okay? And this gives is equal to 0. And the net flux here is 0 because the number of lines entering is equal to the number of lines leaving, okay? So we will now discuss Gauss's law, which describes the relationship between the net electric flux through a closed surface and the charge enclosed by that surface. So consider a positive point charge Q located inside the spherical surface of radius r. Okay, this is a Gaussian surface of radius r. So since the field lines of this point charge are directed radially outwards, right? So those field lines are perpendicular to the surface at each point. Okay. And also the magnitude of E over the surface is constant because each point on the surface is at the same distance from the point charge. So we have for the electric flux integration of E and dA. So we put E out of the integration and we integrate dA, which is equal to EA. And E for a point charge at a distance r is given by this equation. And this is the surface area of the sphere. And so we get, for the electric flux, this equation, okay, if we substitute. So as you can see, E varies with 1 over r square and A with r square. So their combined effect cancel out and we get electric flux that is independent of r, okay? So this shows that the net flux through a spherical surface is proportional to the charge Q inside the surface, okay? And as we said, is independent of R. And remember also that as the magnitude of the charge is larger, if it becomes larger, we have more field lines, okay? So the number of field lines are proportional to the magnitude of the charge. Um, uh, so also we have this figure here. It shows that the number of field lines through the spherical surface is equal to the number of field lines through the non-spherical surfaces. Okay? So we may conclude from this that the net flux through any closed surface is independent of the shape of that surface. It depends only on Q, the enclosed charge within that surface, uh, and is independent of the position of the charge within the surface. Okay, so this charge can be located anywhere. Still, we have the net flux is equal to Q in over epsilon naught. Okay. So if the point charge, also consider this case, if it's located outside the surface of an arbitrary shape, the number of field lines entering the surface is equal to the number of field lines leaving the surface, and the net flux should be zero, right? It is equal to zero. And this is consistent with Gauss's law because the net charge inside this surface is zero. Q in is zero, so the flux is equal to zero, okay? And consider also this case, if we have two charges, then the net flux is equal to Q in, the net Q in. So the net Q in here is Q1 plus Q2 over epsilon naught, okay? So Gauss's law states that the net flux through any closed surface is equal to this equation. Okay, this is Q in is the net charge inside the surface, and E is the electric field at any point on the surface. And the surface used is known as a Gaussian surface. It is just a mathematical surface and it does not need to coincide with any real physical surface. Okay. As we shall see, Gauss's law can be used for a discrete or a continuous system of charge, and it is useful when there is a high degree of symmetry, such as charge distributions that has a spherical, cylindrical, or plane symmetry, and which allows the surface integral to be simplified and for E to be removed outside of the integral. And this can be done by choosing the right and appropriate Gaussian surface that takes advantage of the symmetry, okay? So when choosing a Gaussian surface, it is useful that, at least, every portion of the surface at least can satisfy one of these conditions, okay? The first condition is that the value of the field is constant from symmetry over a portion of the surface. So not necessarily the whole Gaussian surface, but at least a portion of it, the value of the field is constant from symmetry. Another condition is that E and dA vectors are either parallel or perpendicular for that portion, and also that E is zero. In this way, we can really simplify the integration, okay? So first, we will consider a spherically symmetric charge distribution. So consider an insulating solid sphere of radius A and uniform charge density ρ, okay, and total charge Q. Because the charge is uniformly distributed, it has spherical symmetry, and we can choose a spherical Gaussian surface, okay, of radius r that is concentric with the sphere. So this Gaussian surface satisfies two conditions, 1 and 2. First, the electric field is constant everywhere on the surface, okay? And second, E and dA are parallel here because this direction of dA and this is the direction of E. So this Gaussian surface takes advantage of the symmetry. And so as you can see here, the first case, we are calculating the electric field using Gauss's law outside the sphere for R greater than A. So E can go out of the integral because of this symmetry. So we simplify the integration, and A, the integration of the spherical surface is 4 pi r square, and this gives us E is equal to Q over 4 pi epsilon naught r square, which is identical for the one obtained for a point charge, right? So we want now to find the magnitude of the field inside the sphere. So again, we will choose a Gaussian surface of radius r that is concentric with the sphere. So let V dash be the volume of the Gaussian sphere, and Q in here is different than in this case. So Q in here include only the charge within the Gaussian surface, which is equal to rho V dash, okay, equal to this. And we calculate the electric flux, and again, E goes out because it satisfies these two conditions. We can put it out of the integration and we can calculate E. So if you substitute Q in from this equation, you get E is equal to rho R over 3 epsilon naught for R less than A, okay? So this equation shows that as R goes to 0, as we approach the center of the sphere, the electric field approaches 0. And also at the surface of the sphere, where R is equal to A, we get this expression, which is KEQ over A square, okay? So, we will now consider the example of a continuous cylindrically symmetric charge distribution. So let's consider a line of positive charge and infinite length and of a constant charge density per unit length lambda. Because the line is infinite, the field is the same at all points that are equidistant from the line, regardless of where we choose the vertical position, right? So there are no edge effects here, okay? Also, because the charge distribution is uniform, it has a cylindrical symmetry, and we can choose a cylindrical Gaussian surface of radius r and length L that is coaxial with the line charge, okay? And so for the curved part, this curved part here, E is constant in both magnitude and direction, and it is perpendicular to the surface at each point. So it is parallel to dA, right? For this curved part of the Gaussian surface. For the top and bottom parts of the Gaussian surface, the flux is 0 because E is parallel to the surface, okay? For these top and bottom surfaces. So we can, so we have the electric flux includes only the curved surface. So it's Q in over epsilon naught, which is lambda L over epsilon naught. And the curved surface area is 2 pi r L. And this gives E equal to lambda over 2 pi epsilon naught r, okay? So if the line is not infinite but has a finite length, there will not be enough symmetry to use Gauss's law because the magnitude of the electric field is no longer constant over the surface of the Gaussian cylinder because the field near the ends of the line will not be the same as the field for points far from the ends, and its direction near the ends will not be parallel to the surface as in the case of an infinite line, okay? But it can have a component that is perpendicular to the top and bottom surfaces, okay? So it won't be parallel, it can have a component that's perpendicular to these top and bottom surfaces. But even for this finite length line charge, for points far from the ends, this equation can give a good approximation for the field. Okay. You can also use Gauss's law to find the electric field inside inside a uniformly charged rod, and you can also see that it is proportional to R, directly proportional to R. Okay. So we will now discuss the electric field due to an infinite plane of positive charge that has a uniform surface charge density sigma. Because the charge distribution is uniform, it is symmetric, and we can use Gauss's law. Also, because the plane is infinite, the electric field is the same at all points equidistant from the plane. Okay, so we don't have like edge effects here. And as you can see, E is perpendicular to the plane; it's directed away from it, and so the direction of E on one side is opposite to its direction on the other side. Okay. So we will take a Gaussian surface that is a cylinder of area A, which is a cylinder that is perpendicular to the plane and whose center is at the plane, and we see that E, for this curved part of the cylinder, E is perpendicular to dA vector, right? So the flux through this surface is zero, so this curved surface will not contribute to the total field. And we are left with these two faces here, in which E is constant in both magnitude and direction, and it is directed parallel to dA. Vector, right? So the total flux through each end is EA. So the total flux, including the two ends, is 2EA, and this is equal to Qn over epsilon naught sigma A over epsilon naught, and this gives E is equal to sigma over 2 epsilon naught, which shows that it is independent of the distance from the plane. Okay. So E is equal sigma over 2 epsilon naught at any distance from the plane and is uniform everywhere. Okay. So we will now discuss conductors in electrostatic equilibrium. So as we discussed before, a conductor has free electrons that are free to move about the material, right? And these free electrons are not bound to any atom. So if there is no motion of these free electrons other than thermal motion, okay, then the conductor is said to be in electrostatic equilibrium. And in that case, it will have the following properties. So first, the electric field is zero everywhere inside the conductor when it is in electrostatic equilibrium. And this applies even if the conductor is hollow or if it's solid. This is because if the field is not zero, the free charges would accelerate under the influence of the electric field, right? So we will no longer have electrostatic equilibrium. So the field must be zero everywhere inside the conductor, okay? To understand this point further, consider the example of a conducting slab placed in an external electric field E. So before we place the slab, the free electrons are uniformly distributed throughout the conductor, right? But after we place it in the external field, the free electrons accelerate to the left here. So they accumulate to the left at the left surface, and they leave a resulting positive charge on the opposite surface, right? And this will create an additional electric field inside that opposes the external field, okay? So the surface charge density will increase until the internal field cancels out with the external field, and the net field inside is zero. Another property of a conductor in electrostatic equilibrium is that if the conductor is isolated, the charge resides on its surface, okay? And this can be shown using Gauss's law. So if we draw a Gaussian surface inside the conductor, okay, so this dotted line is the Gaussian surface, and we make it as close to the surface as possible. Then, since the electric field inside the conductor is zero, it follows from Gauss's law that the net charge inside the Gaussian surface is zero, and so any net charge on the conductor will reside on its surface, right? The third condition for a conductor in electrostatic equilibrium is that the electric field at a point just outside the conductor is perpendicular to the surface and has a magnitude equal to sigma over epsilon naught, and sigma is the surface charge density. And we can show this by taking a small cylindrical Gaussian surface with its two faces parallel to the surface of the conductor, and where part of the cylinder is just outside and the remaining is inside. So because the conductor is in electrostatic equilibrium, the field is normal, so perpendicular to the surface, okay? Otherwise, if the field had any component that is parallel to the surface, the free charges on the surface would feel an electric force, right? And they would move, and the conductor would not be in electrostatic equilibrium anymore, right? So the net flux through this Gaussian surface is equal only to the flux through its outer face, because E is parallel to the curved surface here. So the net flux through this one is zero, and also E is zero inside the conductor, so also the flux through this face is zero. So we get for the flux EA a Q in over epsilon naught, which is equal to sigma A over epsilon naught, okay? And this is the field just outside the conductor. And the fourth condition is that if the conductor has an irregular shape, then the charge density is greatest at places where the radius of curvature is smallest. And we will discuss this point in another video, okay? So we will now consider the example of two oppositely charged parallel conducting plates. So consider two large conducting plates of equal and opposite charges. So the surface charge density is plus sigma and minus sigma here. And we want to find the electric field in the region between the plates. And as you can see, in this region E is constant in both magnitude and direction. So this configuration is a way to achieve uniform electric fields, okay? So most charges accumulate on the inner surfaces here, and a small amount of charge reside on the outer surfaces. So if the plates are really large, this outer charge is negligibly small, and in this case we can assume the field to be uniform in this region, and that the charges are uniformly distributed over the opposing surfaces, okay? So as we saw in the previous example, the electric field due to each sheet, the positive or the negative, the magnitude of this field is equal to sigma over 2 epsilon naught. So in the region in the middle, they have the same direction, so they add up. So the total electric field in the middle is given by sigma over epsilon naught. And in the regions outside, they have opposite directions and they cancel out. So the field outside for really large plates can be approximately zero, okay? So I included the three solved examples. So thank you for watching. Please don't forget to like and subscribe, and see you in the next video.